What we want to do right now is continue our discussion of number sets and really our last set of numbers, which will be complex numbers. And complex numbers, like real numbers were combined with rational numbers and irrational numbers, are really a combination of two types of ideas. Complex numbers are real numbers and imaginary numbers combined. And what we want to do is look at what the need for these were. Now, in algebra, we end up with this idea that we can get a solution that looks like this, and if we go to solve it, we get something that doesn't work with real numbers. The square root of -1 does not exist in real numbers, but this form is important for the fundamental theorem of algebra. When we go to factor large polynomials either break down into something that's linear, right? You can get a collection of roots that when we multiply them together, in this case, right, that was a quadratic form, and R1 and R2 would be the solutions to them. Or we got things like x squared plus 1. And so all higher order polynomials were either irreducibly quadratic, which had two imaginary answers, or linear, which had these. And the power determined this. I could make a cubic, right? X squared plus 1 times x minus 1 would give me x cubed plus minus x squared. Doing my FOIL here. Plus x minus 1. And so this could factor down. But you need to know that there are imaginary roots in there. And so this created kind of a theory of complex numbers that made algebra work. So what happens is we have to define -1 to be I. And when we do that, we can write any number. So we'll say the set of complex numbers is any number A plus BI, such that A and B are real numbers, and I is defined as the square root of -1. So we have this new set of numbers that can solve this problem, that can give us these anchor pieces for the fundamental theorem of algebra. And so complex numbers are really the last number, so to speak. I guess, in some mathematical theory, we have other sets of numbers coming through. But if we look at this, if b equals 0, then the complex number is just a real number. And if a equals 0, then it's an imaginary number. Though there can be some number that has parts that are both imaginary and real. And so what we'll say is this is the standard form of a complex number, and it will have a real part and an imaginary part. And a good rule of thumb for how these things map into reality, real parts we can measure. Imaginary parts aren't measurable, so they don't manifest themselves in solutions that are measurable, though they do affect things. Electrical engineers have to take into account the imaginary parts of oscillations. Quantum mechanics rely on imaginary numbers, and solving in general algebraic equations require us to have an idea of what the imaginary and complex solutions are doing. Euler, who kind of gave us the term imaginary part, imaginary. He regretted that later. Did a lot of algebra with complex numbers, and we're going to sum up some of the things that were noticed from here. So we can say that in this case, for the standard form, the real part will be a, and a scripted I will be b. So we can talk about these as some function pulls out the real part and some function pulls out the imaginary part. Now, one of the things Euler did was he made an axis of the real part and the imaginary part. And this is something that we'll see that we can algebraically deal with this as them being not like terms. And we'll discuss more and more the idea of making these things orthogonal. So however much you move in the real direction doesn't affect how much you move in the imaginary direction. And so we can think of these imaginary numbers as having this existence in what we're going to call the complex plane. And some things kind of intuit out of this. There's a mirror image where if I come down negative b, I still have a in the x direction, and I've moved a negative angle. And so these two things are closely related, and that's called the complex conjugate. In our standard form, if z is a plus bi, then in the complex conjugate, we change the sign of the imaginary part. And we're going to use this over bar to represent a complex conjugate. Some things to note out of this. We can talk about the length or the absolute value as being the length here. So what we'll say is that the absolute value or the magnitude is the length of this vector that exists in the complex plane. And because this vector is a right triangle, the Pythagorean theorem works. We get a squared plus b squared square rooted as the length or the magnitude. And so we have some relationships that let us do arithmetic with complex numbers. So some things that come out of this immediately from this form. If I have one complex number and I add to it a completely different complex number, well, I can collect like terms. The real parts add, and the imaginary parts add to give me a new complex number. And it's still a complex number. I have a real part here and an imaginary part here. If I multiply two complex numbers, well, let's work this out. We'll FOIL. So I get AC for the firsts. My outers give me a DI. My inners give me CBI. And my lasts give me BDI squared. But we know I squared is negative 1. So we get AC plus ADI plus CBI minus BD. Collecting like terms again, I have a real part of AC minus BD, and I have an imaginary part of AD plus CB. And so we can multiply complex numbers and still get a complex number back. If I take a complex conjugate, a plus bi, it's a minus bi, and the absolute value, as I said before, the Pythagorean theorem gives us the magnitude. Now, in each new set of numbers, we have lost things as we went through. Once we developed rational numbers, we lost the ability to divide by 0. or divide by 0 dropped out some numbers that could be possible. And that created some restrictions. There's always a restriction coming across. One of the things that happens with the restrictions here is I can't put complex numbers in order. If I have two complex numbers where they represent by these points, I can't count from one to the other. I move through this space where there's no sense of one is greater than the other. So I can't say that one complex number is greater than another complex number, or vice versa. There's no way to order them, and that's something that the magnitude helps us deal with a bit, but it is something that happens. And you'll see when we have to use inequalities, we tend to go to magnitudes on them. So let's look at some laws. Some of these laws you'll have to prove in your homework. So let me get back up here. So if I have one complex number and I multiply it by another and I get its absolute value, that's the same as multiplying the absolute values themselves together. If I have one complex number and I add another one to it, the magnitude is going to be less than or equal to the sum of their individual magnitudes. And this comes from what's called the triangle inequality. If I have an absolute value and I square it, that's the same as multiplying it times its complex conjugate. And this will become a kind of useful relationship. A complex number times its complex conjugate. Let's see here. If I add two complex numbers and take the complex conjugate of the result, that's the same of adding their individual conjugates. If I take two complex numbers and I multiply them together and then take the conjugate, that's the same as multiplying the individual complex conjugates. And division of complex numbers is the same as the numerator times the complex conjugate of the denominator divided by the magnitude of the denominator squared. And in your homework, you'll work out some proofs for these, as they are helpful relationships for complex numbers. This lets us really fully state the fundamental theorem of algebra now that we have complex numbers, which is if we'll let some polynomial in terms of complex numbers, right? So it has an nth degree. Right, we've seen this from algebra class. When we define a polynomial, you have the degree of the polynomial as the highest power term, all the way down to the constant, and we use these to factor. And so if this is a polynomial and not a constant, polynomial in variable z, with complex coefficients, which are, all the a sub n's. Then the equation, right, when we set this to 0, has n solutions C, and complex solutions. That's factoring, its roots, all of these things end up being the same, factoring and roots. So what we want to do here is explore other forms of complex numbers, and because of the graphing situation on it, we'll look at a polar form, and then we'll do some complex arithmetic. So I'm going to put this up here. In the next lecture, we'll look at the polar form. And so the idea of the next lecture is, if I can define this as r and theta, then I can talk about my complex number being r something theta. So I'm going to think of z as being a function of r and theta, or z being a function of a and b. And so what we want to do is do this polar definition. So I will put that together in the next video, and we'll continue onward.